point D, distance point C. So V as a function of x dx now, right? So we have moment at point D minus by moment at point C is equal to, you integrate x at point D, x at point C. Okay, so this is your Vx dx. Okay, so this will get you your moment equation. Okay, so let's go further. Okay, so after you get your moment equation, okay, we are going to apply, right? We're going to apply. Okay, so moment equation. Then after that, we're going to apply the elastic curve equation. Right. So let me briefly describe what is a elastic curve equation. I'm not going to derive it, okay, but I'm going to tell you what it represents. Okay. So now if we look at the same beam, okay, so we still look at the same beam down here, right? So on the same beam, right? I'm not going to draw the load, but I'm going to just draw the beam over here, right? So this is our point A, and this is our point B, right? The next one is I'm going to superimpose another graph into onto the structure now, right? So this axis over here is your y-axis, right? And this axis over here is your x-axis, okay? And the distance over here, we know that this is your L. So I'm going to roughly sketch, right, the deformation pattern, okay? So if we look at a deformation pattern, this is just a sketch, okay? It will look like this. Okay, so this is our deformation or deflection pattern. Okay. Okay. So let's say we want to find, okay, we want to find at a certain distance, okay, we want to find this point, right? We want to find at that x distance, what is the deflection and what is the slope, right? So over here, as you can see, I'm going to now project a line over here. Okay. And this distance to this distance is our x. X is a variable, okay? Any position, as long as within the L distance. And then we have the other distance over here, the vertical distance. Now this vertical distance represents your y. So y for this case is the deflection of the beam. Okay. And then once you take the point, you draw a tangent line. So I'm going to draw a tangent line. So this is our tangent line. Okay. So it goes this way. This is our theta. Right? So theta is the slope of the deflection. And you can, as you can see, it's derived mathematically in that sense. So anti-clockwise is positive. Okay, anti-clockwise is positive. Okay, so in order to find, right, in order to find the slope and deflection, the slope and deflection the elastic curve method must be used. Okay, as I say, I'm not going to derive the elastic curve method, but I'm just going to write up the expression for you. So it has EI, okay, d squared y over dx squared is equal to m as a function of x. Okay, so you guys say, hey, I've seen this in math before, yes or no? Right? So this is known as the elastic curve equation. Okay, where E is the Young's modulus, right? And then I is the second moment of area. M as a function of x. This is the moment as a function of x, right? And then y is your deflection. Okay. X is the distance along the x distance, okay, not just distance, not just any x distance along the beam. Okay, so now if we were to look into where we stop off before I talk about the elastic curve, we realize that we have a moment equation down here already. Yes or no? So this moment equation is substitute into here, right? So therefore, when we have EI d squared y over dx squared, now this will be equal to what? This will be equal to xd xc, right? You integrate, and then you have what? You have vx dx, right? So you just equal. So this is your moment equation, and then we're going to integrate, right? So now the next one I'm going to integrate is without limits, okay? dy by dx, so it's equal to, when you integrate, okay, so you integrate xd xc v as a function of x dx, okay, and then you integrate again. Then you have to plus by what? C1, because there's low limits. Okay, so this is your integrate number 2. number 3 in fact, right? So this stage, okay, at this stage, we call it apply the elastic curve equation. And then we integrate the 4th time. We have EIY, okay, one, two, three, plus by C1x plus by C2. Okay. So if I'm going to summarize this, right, without deriving, because I stopped down here to go into elastic curve. Okay, just to quickly to summarize. So in summary, with this method, right, we start from where? dv by dx. Here, let me in summary, let me write higher, right? It's equal to minus omega as a function of x, right? Then after that, you integrate, right? So when you integrate, you have the shear force equation, right? So minus omega as a function of x dx, right? Then over here, not just dx, you have to plus by c1, because now there are no limits, okay? So integrate number 1. And then you integrate the 2nd time. Right? So you get moment as a function of x, right? And then this will be equal to minus omega as a function of x dx plus by c1x plus by c2. Okay. Then from here, you apply elastic curve method. Okay. So you have EI d squared y over dx squared is equal to m as a function of x, and then the whole function again, and then you integrate the 3rd time. Is very math intensive. I mean simple math, okay, nothing like what you guys are doing if in your math, your 2nd or 3rd year math. Okay, this is easy. So this is EI dy by dx, and this is where dy by dx is also known as the slope. So this is also known as EI theta. So you integrate 3 times after applying elastic curve, plus by c1x squared over 2 plus by c2x plus by c3. Okay, and then finally you integrate the 4th time. You have EIY is equal to 1, 2, 3, 4 minus omega as a function of x. It's not that bad, okay, when we are doing an actual problem. X cubed over 6 plus by c2x squared over 2 plus by c3x plus by c4. Okay. Now the not the problem. Okay, with this method, right? Again, it's not a problem. It's a characteristic of this this method. Okay, it's a characteristic of this method is where, okay, let me tell you what's the characteristic of this method. Is that C1, okay, C1 to C4, you have what? 4 constants. Yes or no? Right? So we are given